Okay, good afternoon, everyone. So we are going to talk about Bayesian parameter estimation today. This is the second part of our discussion on parameter estimation. Last time we talked about maximum likelihood, which doesn't assume any prior knowledge. So today we are going to assume some prior knowledge and see how this prior knowledge is going to help us in estimating the model parameters. Now, to remind everyone where we are in this part of the semester, we are actually in the middle of part 2 of our course, which studies about classification methods. And then we are using this general principle, which is called the linear discriminant analysis, and within which we are looking at this generative models, meaning that we are going to look at the data and then come up with a model, estimate the model parameter, and then we define the separating hyperplane. Afterwards, we are going to spend some time talking about those discriminative methods, which doesn't really rely on models. Okay, so you are going to define the separating hyperplane strictly from the data set. Okay, so today's outline is as follows. We are looking at this topic of Bayesian prior, and then there are two parts. I want to spend a majority of the time motivating the need of doing this Bayesian estimation and tell you what are the pros and cons and what are the computational benefits and so on. So we will talk about this posterior, we talk about 1D illustration and try to interpret these results. And then I will spend the remaining maybe 15 to 20 minutes to talk about how do we choose a prior. That really depends on what model that you're working on. In our case, we're working on Gaussian models, and so we can ask what would be the prior for the mean, what would be the prior for the variance. And this discussion follows from a very, very big topic called the conjugate prior, which you can find in the machine learning textbook. So I will try to link these two to this concept here, and then I will point you to the related textbooks for further readings. Okay, so the difference between maximum likelihood estimation, the thing that we talked about last lecture, and then maximum a posterior estimation, so their full name is stated here. The difference between these two is the presence and absence of a generative process. Okay, so in the maximum likelihood estimation procedure, you are really treating this theta as a fixed but unknown parameter. Once you know the parameter, I can draw samples from this distribution. So it is literally a distribution of x parameterized by this number theta. Okay. Now, in the Bayesian setting, this theta is no longer a fixed quantity. It's no longer a deterministic quantity. It is a random variable by itself. Therefore, you will have a distribution of theta. And therefore, you can say, what is the prior distribution of theta? From this prior distribution, okay, so you have another distribution. From the distribution, you're going to draw a theta out of that. And when you use this theta to generate the x. So there's a two-layer generated process for the Bayesian approach. Now, there are, of course, benefits and disadvantages using either of those, which we're going to investigate in this lecture. All right, so to make this concept a little bit clearer, I want to first describe the concept, and then I want to use some examples to illustrate this concept. So the bottom line message is this. In the maximum likelihood, the parameter is deterministic. Now we are going to assume that theta indeed has a distribution, and so now theta becomes probabilistic. So what I mean is that now the theta, so you remember in the previous slide you have px given theta, right? So x given theta. There is now a distribution for the theta. So you assume that theta is a random variable, then you can ask, how does the theta look like, right? So you have p theta of theta. So now p theta is a distribution of the parameter theta, and so this random variable has its own mean, it has its own variance. Now the distribution of the theta can look like a Gaussian. It doesn't need to look like a Gaussian. Okay, you can draw another distribution. You can say that this is my p theta. which means that I have a higher chance of selecting a theta coming from this range. I have a lower chance of selecting a theta from this range. Okay. All right. So if you're still puzzling, let me draw you an example. Okay. So imagine that you go to I-65. Okay. Imagine you go to I-65. So you see a car. All right. So you see a car, and then this car is driving at a certain speed, and then suppose you are a police car, and of course you will put out your radar and then try to estimate the speed of this car, and then what will happen is that the government is not rich, and so the government wants to cut the budget, and so they just buy you a very, very cheap laser gun. Okay, so the laser gun has certain limitations. It has a lot of uncertainty. So if this car is coming at a speed of 70 miles per hour, and then the laser will say that, look, this is maybe 75 or 65. Usually it's over speed so that they can charge you, right? So they will say it's 75, so I'm gonna charge you. Now there's certain uncertainty, right, associated with that device, that radar. Okay, so suppose you are indeed at a theta, right? And then the radar will say that you have certain distribution. That is the measurement obtained by the radar. Okay, so that is px of theta x given theta. Okay, so theta is your mean, and then x is actually your sample. Okay, so you're saying that okay, x is the measured speed, theta is the actual speed. Okay, so now you have the actual speed, and then there is a measured speed. The measured speed, because of the uncertainty of the device, you have certain distribution. Is that clear? All right, so you have x and theta. Okay, so if you use the maximum likelihood estimate, what you're going to do is that you're going to take multiple measurements of x, and then you are going to estimate the theta. That's the maximum likelihood estimation. Okay, take multiple measurements and try to make your best guess of theta. Now, in the Bayesian world, the thing is a little bit different, just a little bit different, because it really depends on who's driving that car and what kind of car it is, right? So I have been always joking to my students that it is extremely eye-opening if you go to an undergraduate garage, okay, compared to a faculty garage. It's very eye-opening that you can see many, many interesting cars on this campus. And so you can imagine what kind of speed that kind of cars will be on I-65. And so now you will also have another layer of uncertainty. That uncertainty is associated with what kind of car that you're looking at, right? So on one day, you are looking at an undergraduate student. Okay, I'm sorry, undergraduate student, but I'm just making an example, okay? Don't feel offended. So if it's an undergraduate car, and then that car is a little bit pricey, okay? And then you do want to utilize the speed of your car, and so you will be driving at a certain speed that is more than normal, okay? And so that would be the speed. That would be the actual speed, okay? So the actual speed is not necessarily 70 miles per hour. It could be higher, it could be lower, right? So if you look at my car, I have a very big van. I cannot drive very fast, otherwise my wife would be unhappy, right? So then my speed would be different from the actual speeds. Okay, so what does it mean? It means that there is another distribution of the actual speed. What is the distribution of the speed? Well, it could be like this. It depends on how do I drive, what kind of car that I have. So you have a p theta of theta, okay? If let's say the average speed is here, and then you can say that, look, I have a much better car, and so I'm going to operate at this point. I'm maybe operating at this point. It really depends on the particular stage of the theta that you have, right? Now, you will have two layers of generative process. The first process tells you that what is the underlying distribution of your theta. The other distribution says that now you give me the theta, and then I'm going to use a device, which is not very, very good device, and that device has uncertainty, and so it gives you px given theta. So you have two layers of uncertainties, all right? So now you say that, give me a set of xn's, I have a bunch of measurements, find out the best guess of your theta, okay? So then you can say that, hey, this is a college town, so there will be more students than faculty, and so it's more likely that your theta has certain intrinsic bias towards a certain speed than the other part of speed, right? So that is the prior information you can put into your problem formulation, okay? And that will actually change your estimate, because without this prior knowledge, you are just going to take the average. If this is a Gaussian, as we have shown before, you're going to take the average and you will say that average will be the actual speed. It will be the best estimate of the actual speed. But since you know that it's a college town, more students are driving very, very good cars, and so there will be a shift towards the high speed, then your estimate of the theta should perhaps be biased when you don't have too many measurements. Now, although when the number of measurements goes to a very big number, then of course you want to rely on the measurements rather than your prior knowledge. But in the absence of, when your number of training samples is few, then you may want to leverage some of this prior knowledge when you're trying to do your estimate. Okay? So that's the principle behind the Bayesian. You ask Bayesian, there should be a subjective component. Where does it come from? It comes from here. It comes from another distribution that generates the parameter. All right, so so what is the formulation now? Well, the formulation now becomes the following. We are going to use the thing called the Bayes theorem again. The Bayes theorem says that if I have this posterior distribution of theta given xn, then I can write it in terms of the product of x given theta times p theta divided by xn. Okay, so this is a Bayes theorem. And now, if I want to, instead of maximizing the likelihood function, let's say I want to maximize the posterior distribution, then what happens is that I'm going to formulate this argmax problem of theta given all these data points coming from the data set D. Since I am assuming that every element in this D is independent, then I can write it as a product of the individual posterior probabilities. Then you can see that this posterior, according to the Bayes theorem, you can write it in terms of this ratio. And look at this, the denominator only contains x, and the x has nothing to do with your optimization variable, so you can ignore that. That won't change the optimizer. Now, when you have this p theta of theta here, you realize that that's just like doing like a regularization to your problem. In what sense? Well, if you take the negative log onto this equation, okay, put negative log there, then the negativity will change the maximum to minimum, and then the log is monotonic increasing, so it won't change the maximizer, and so you can just put a log over here, then you can turn this product to a summation, and then individually you will have the two logs. This is just the log of the likelihood. This is the log of the prior. So essentially, you're just adding one additional term to the maximum likelihood estimation. Okay? So this is, you can treat it like a regularization. Okay? I will come back to this point in the next lecture. Okay? How do we view this as regularization and what is the meaning of that? We'll come back to this point later. Okay, so now, once we have this formulation, what we can do is the following. We can look at a very, very special case, and we ask, in what situation will this maximum a posterior estimation problem go back to the maximum likelihood by choosing what kind of prior that I can make this formulation exactly the same as maximum likelihood? Well, you can consider this special case when this p of theta is indeed a delta function of theta minus delta theta of theta 0. Okay, theta 0 is some deterministic quantity. If you make that assumption, you can put this p theta into here, all right? Then what will happen is that you can look at the log of this p delta, okay? So log of this p will either be log of 0 or log of this delta. All right, so now what is the delta function? This delta function, by definition, is 0 everywhere, except when you are at theta 0, then you have an impulse. Okay, so this is a delta function. So you have 0 everywhere. Now, if you take the log on all these zeros, you get minus infinity. Okay? As long as theta is not equal to theta 0, you get minus infinity. However, if you are at theta 0, now the value at theta 0 is actually 1. Okay, so you can think in that way. So this is 1. Then if you put a log of a p theta of 1, then you get 0. Okay, so when theta equals to theta 0, you get 0. So you plug this into this minimization problem, then what you will have is this arc mean of negative summation of minus infinity when theta is not equal to theta 0. But if it is indeed theta 0, then you will get back the log likelihood term. All right? So, but if you look at this problem, right? If you look at this problem, since you have already chosen theta to be exactly at theta 0, then the solution has to be theta 0. Okay? So you have already said that I am absolutely certain that my solution is theta 0, and therefore I am going to choose my solution to be a theta 0. Okay. Now, the other opposite would be that I have no preference of my solution. Okay. So then, in that case, you can say that my p of theta is just uniform across whatever range of theta that I am interested in. Okay, so if you put that in, then you can see that that theta, okay, will become like a constant. It doesn't change with theta as long as your theta is within the support set that you are considering. Okay, so now it becomes a constant. Then this term doesn't really have an effect as long as your theta is inside the set, right? So the effect is gone. Then you will just have this minimization over the likelihood function that will go back to the maximum likelihood estimation. Right? So you can see that by choosing a different prior, you can swing between a maximum likelihood estimate all the way to no estimation at all. I just trust my solution to be theta 0 because I'm absolutely certain that there's no uncertainty about my theta. The distribution of theta is just a delta function adds a deterministic quantity theta 0. Okay, so now you swing between uncertain all the way to absolutely certain. Okay? So that swing is the power offered by the Bayesian approach because you can switch from one side to the other by choosing a different prior. All right, so now let's spend some time understanding the picture of this maximum a posterior estimation. How does this prior play a role in my estimation problem? So this is the exact same problem as before, last lecture. Okay? In last lecture, we have this likelihood function, and then we look at the case when there's only one sample, and then we say that, okay, the best estimate is a Gaussian that matches the center of your sample. But now, in this problem, when we have a prior, we want to understand how this prior will interact with my estimation procedure. So let's start with the case where you only have one data point, again, in a 1D setting, okay, one data point. Then the maximum a posterior problem says that I am going to maximize this posterior distribution, which is essentially trying to solve this maximization of x minus theta, and then there's another term. Okay, this term comes from the prior. Okay, this prior, what is the prior? The prior that I'm assuming is another Gaussian. Okay, don't question me why I'm choosing Gaussian. I will tell you later. Okay, but I'm just choosing a Gaussian. This Gaussian is a Gaussian of the theta, right? So in this problem, you have a known parameter, and this theta is the mean. So I'm assuming that the sigma is known. Okay, so theta is an unknown parameter. I want to estimate there is an underlying prior distribution of the theta. This theta has its distribution of center as theta 0 and sigma 0. Okay, so that is the prior distribution. So once you know that the distribution of this p theta, you can plug it in here, then the maximization becomes this. Okay? Now, if you want to go back to maximum likelihood, just ignore this term. That is the maximum likelihood estimation problem. Okay? The difference is that now you add another term that comes from your prior. So what has become different? We can take the derivative, setting it to 0 with respect to theta. Then with a lot of calculations, you can show that the solution will look like this. Okay. Let's look at the diagram. First of all, we have a data point marked by this blue dot. That is your data point. You only have one data point. It's a 1D problem, a data point. Now, without knowing the Bayesian approach, you are going to slide this Gaussian function left and right until a point that you can best explain the presence of this blue dot. It happens when this Gaussian has a center overlapping with this blue dot. That is the maximum likelihood we explained last time. Now, with the prior, what it changes is this. I am going to add another green curve. Okay? The green curve says that without even knowing the presence of this blue dot, I have a preference, okay, or I have a belief that my solution should be located somewhere around here. Okay? Without knowing the presence of this blue dot, no blue dot at all, I have already determined that the solution has to be distributed according to the green curve. That's the prior knowledge, because you look at the term, the prior distribution, it has nothing about x, right? So it's independent of x. It doesn't care about your x. It doesn't care about your measurement. It's just your prior belief of what the solution should be. So that is the green curve. Now, when you add the two up, okay, so now you add the two, you add the influence of the blue dot and also the green curve. The blue dot will say that, look, your red has to be overlapping with me. The green curve says that I think the solution should be somewhere there. And so the solution obtained by solving this maximum a posterior is somewhere in the middle, right? You're not totally relying on the blue dot anymore. However, you're not just using the green curve. If you're just using the green curve, it's not an estimation problem. You just look at the prior, right? Okay, so the solution will be somewhere in the middle. And you can see that the location of this green curve actually has a lot of influence if you don't have a lot of data points. The green curve, if the green curve is somewhere here, then your solution will be somewhere in the middle. Because the green curve says that I prefer the solution to sit on the right-hand side. And although your measurement is there, I don't fully trust you. And so let's compromise. The solution will be somewhere in the middle. This is actually reflected by this equation here. This equation says that my solution, which is my best estimate according to my posterior distribution, it will be a combination of my x and theta 0. Okay, you can ignore all these other terms. That's literally just x and theta 0. Okay, so that the two players, x and theta 0. X is your measurement, theta 0 is your prior. And then you're going to form a weighted average between the two. Now, how do I see this as a weighted average? You can treat the first weight as this. Okay, so this would times x, and then you have theta squared, sigma squared divided by sigma 0 squared plus sigma squared times theta 0. Okay, so now it is really a weighted average because these are the two weights. You add the two weights up, you get 1. So that's really you're drawing a line. Okay, so you're drawing a line. A line says this is x, this is theta, and then I'm going to look at somewhere in the middle, and then the distance is determined by this ratio. Okay, so now let's see what is the influence. Well, the influence is really depending on which one is stronger, right? So theta 0 measures what? Theta 0 measures the uncertainty of your prior, and sigma 0 measures the uncertainty of your prior, and then sigma measures the uncertainty of your measurement. Okay, if your uncertainty of the prior is big, right? You're not too certain about your prior. You don't trust your prior at all. Then you can see that this term will be big, right? Because if sigma 0 is big, then the influence of sigma is small relative to sigma 0. So this term will be closer to 1. And that makes sense because the solution will say that this will be big, that will be small, so you will rely on x. X is your measurement. If you are not too certain about your prior, use the measurement. Okay? Vice versa, this is sigma squared. This is the uncertainty about your measurement. If you're not very certain about your measurement, then you better use your prior. Okay? This is like your belief of the speed of a car versus the radar that you use on your police car. So which one is more reliable? You just use that one, okay? And then that is giving you a very simple linear combination. So this is a slide summarizing what we have just discussed, okay? So you're looking at this term. Now, if in the ideal case where sigma 0 is indeed 0, then you can show that this term will go to a theta 0. So there's no uncertainty, absolutely sure that theta is theta 0, okay? Sigma 0 equals to 0 means like there's absolutely no uncertainty about your prior, okay? Your prior is a delta function, and therefore your solution is theta 0. On the other extreme, if theta 0 is infinity, so it's like a uniform distribution, then your theta should just become x. You ignore the prior, just use the measurement. All right? Okay, so so this last comment is pretty useful. Map solution gives you a trade-off between the data and the prior. That is the thing that's offered by the Bayesian approach. Now, let's try to work a little bit harder on the case where n equals to 2. When n equals to 2, in terms of formulation, is exactly the same. Okay, you just have two data terms, and so this is the minimization that you're considering. So you have three terms. You take the derivative, set it to 0, and then you are going to get this expression. Okay, this expression is not too complicated than the one sample case. What does it say? Well, it says that now your sigma 0 has to go with the sum of the two measurements. Okay, and then your theta 0 has to go with sigma square. And so now you can break it down into two cases again when you're absolutely certain or you're absolutely uncertain. Then if it is absolutely certain, then you can show that this theta will go to theta 0. But you have a useless prior, then you can show that theta equals to x1 plus x2 divided by 2. What is this result? This is maximum likelihood, right? So if you have a useless prior, you actually get a maximum likelihood estimate. But if a very useful prior, you will use the prior. The Bayesian approach is somewhere in the middle. By tuning the number of sigma 0 and sigma, then you're in the middle between your measurement and also your prior. Now, we can ask the next question. What if you have a really, really, really large n? What will happen? So we can follow the exact same procedure. Then the maximization becomes this. Now you have a summation of all these quadratic terms. You solve this problem by taking the derivative setting to 0, which I'm skipping here. You can get to this form. Okay? It's a little bit complicated, but indeed, it's in the same form as before. Now, how do we interpret this result? You look at here. You have a summation of all these data points, and then in the bottom, you have this n here. You can ask yourself, what will happen if my n grows, right? Meaning that if I have a lot of measurements. Now, if you have a lot of measurements, you look at this term. You have a sigma square summation of xn, which is this term here, and then you have theta 0 times sigma squared divided by n times sigma 0 squared plus sigma squared. As n going to infinity, as you have more and more samples, who will dominate in this equation? This is a constant, and of course the summation will dominate eventually because you have lots of samples, right? This number will become big, and so this n will become big. What will happen? The influence of this term and this term will be gone. Okay, so now you can ignore these two terms when n is big, right? Then you have sigma 0 squared times this divided by sigma 0 squared times n. You can further ignore this sigma 0 squared because they're common on both the denominator and numerator. Then you get this result. What is it? This is just the maximum likelihood solution. It says that as you have a lot of measurements, don't bother to look at your prior distribution because you have enough measurements. Just use your measurements. That will give you the best estimate. Okay? That also tells you a very useful thing, that when should you use the Bayesian approach? You should use the Bayesian approach. It will become useful when you don't have enough measurements. If your prior is good, and if your measurement is not a lot, then the Bayesian is going to help you. Now, of course, you can, you will get screwed if your prior is bad. If you choose a really crappy prior, and then you don't have enough measurements, that will give you an even worse estimate than the maximum likelihood. Right? So there's no promise that by using a Bayesian is always better. It's only better when you have a reasonable prior to start with. Okay? Then where does the prior come from? It comes from your prior knowledge. It comes from your experience. It comes from the domain expertise on your problem, that you know that I'm working on this problem. I have this temperature. It has to live in a certain range. And outside this range, it becomes unreasonable. That's your domain expertise. That's your domain knowledge. You want to apply that domain knowledge into your model, and then you apply the Bayesian approach, then you will have a better estimate when you do not have enough measurements. When you have enough measurements, then hopefully your prior influence will be gone. Then you will just rely on the measurements. So this slide summarizes what we have just talked about. If you set n going to infinity, then your estimate will take this form. Okay. Eventually, after doing all these calculations, you can show that your theta will become this 1 over n times all the summation of xn's. And then on the other extreme, when n goes to 0, then you can cancel out a lot of terms. Then you can show that your theta has to be theta 0. Okay, so when will this happen? N goes to 0 means that you don't even have a measurement at all. Okay, you haven't ever go to the lab bench and collect the data. Then what should be the estimate? Just use your prior knowledge. Okay, so that is the interpretation of this result. Okay, so we can also ask the question. Can you show me what is the posterior? Posterior distribution meaning that I'm looking at this parameter mu given the data set. How does this posterior distribution look like? Because now it's just Gaussian. A product of Gaussian will become still a Gaussian. So you can show that the posterior distribution takes this form. Is given by this equation, and then your posterior mean is given by the maximum likelihood mean times the prior mean, and then there is also a posterior variance is given by this equation. Okay? Now, how do you show this result? This is literally doing that mu given data is just the probability of d given mu times the probability of mu. You multiply these two equations up, and then solve a very tedious expansion, and then collecting terms, and then cancel out the terms. Then you will get to this equation. Okay, it's a quadratic equation, so sum of two quadratic equations is still a quadratic equation. It remains a Gaussian, all right? And so you can show that the mean of this distribution is it has a mean of mu n. It has a variance of sigma n. Now, pictorially, what it means is this. Suppose I really generate the data from a distribution of mean 0.8 variance of 0.1. Okay, so that is my data set. And then if I do not have any measurement, then I will just follow my prior distribution. The black curve is my prior distribution. Okay. Then as I have more and more data points as n grows, my posterior distribution, okay, I'm not talking about the likelihood. The likelihood still does, okay? The posterior will be distributed according to this equation. It has its own mean, it has its own variance. It's just the product of the likelihood and also the prior. The posterior distribution will become different. It will change when the number of samples increases. Okay, so when n is 0, you just rely on the prior. As n grows, you can see that this posterior distribution will approach to the distribution that you want, right? And so you ask, hey, what is the best fit to my data point according to my posterior distribution? The posterior distribution will say that, look, you should actually choose this curve, okay? And then the location will be somewhere here. Right? So this change of the posterior distribution is what is variable for the Bayesian approach. Okay, so Bayesian approach, by adding this prior, and then by multiplying the prior with the likelihood, you are essentially changing the posterior distribution as n grows. Okay, any questions so far? Now, if not, let's discuss a even more challenging question of, okay, so you have shown me the benefit of using a prior. Okay, so the benefit of using a prior is that when I do not have enough training samples, then the prior is going to help me find a better estimate using my prior knowledge. But how do I choose a prior? Can you give me some examples of choosing a useful prior? Now, this is a very deep question, and that again has to go with your specific problem if you want the best answer. Computationally, there are some rules of thumbs that you may want to consider. And the rules of the thumbs really is really based on the computational convenience. Okay. It may not be based on any physical interpretation of your specific problem. It's just based on the computational convenience. Let me explain what I mean by computational convenience. So there are multiple parameters in a Gaussian setting. There's a mean, there's a variance, so you can put the prior for the mean, you can put the prior for the variance, right? So let's look at the mean case first. So if you have a mean, you want to put a prior of the mean, what we have just shown before, okay, so the 2 pages before, is that suppose this is your likelihood is a Gaussian by your problem definition. If you choose the prior to be also a Gaussian, then you can show that the posterior distribution is also a Gaussian. Now, you may think that this is so nonsense, okay? A Gaussian times a Gaussian becomes a Gaussian. Yes, this is very important, okay? Why are you choosing the prior of the mean to be Gaussian? It's literally because that you want the likelihood multiplied with a prior will remain the same distribution. Why? You want convenience. You don't, okay, if you change this to some complicated distribution, steady change distribution, you multiply that, and then you want to calculate the mean, it's just extremely tedious, right? Now, if it is a Gaussian, you multiply 2 Gaussian, it's still a Gaussian. It's just a little bit work, and then you can still find out the mean. You can still find out the variance in the exact same form, right? So that will motivate the use of a prior distribution that takes the same form as the likelihood. Now, that's not always the case. I'm going to show you something else, okay? What you really, really want is that you want the likelihood to take certain form. You want the posterior to also take a similar form so that you can obtain the mean and the variance easily. Now, is this choice good? Not necessarily. It really depends on your problem, okay? If you have a much better sense of your problem, you have physics behind, physics always more useful than all these machine learning, okay? So you want to trust your physics. But in the absence of any other expert knowledge, then you may want to consider these computational approaches. Okay, so now let's consider a little bit more complicated case when your prior is for the sigma square, no longer the mean. Okay, so suppose that the mean is already known. We ask what would be the reasonable prior for the sigma square? So the mean is fixed. The variance is now changing. So there's a prior for the mean, for the variance. So in this case, you can write down the likelihood with respect to your variance. So I change, I don't want to call it sigma square, I just call it 1 over sigma square as lambda. So now you have the lambda here, you have lambda there. Then you can write this equation into this form. Okay, it's just exactly the same as before, but I just replace your 1 over sigma square by lambda. Okay, so I want to find the likelihood in terms of the lambda. It's in this format. All right, so what kind of prior that I should choose so that when I multiply my prior, p lambda, with this likelihood, d given lambda, it will stay in the exact same form. Not necessarily the same number, but same form. You recognize this. This is what? This is some constant. I call it a. Okay, some constant a times lambda to the power something, lambda to the power something, exponential, minus lambda, times some constant, right? So now you may say, how can this ever be a useful prior? Yes, I'm saying that this is computationally very efficient. I'm not saying that it's justified by physics, okay? It's computationally extremely efficient because if your prior, p lambda, takes this form, you multiply that with your likelihood, you will obtain the same form. Don't believe me? Okay, plug this in. You just have n divided by 2 plus b, and then you have this constant plus c. That's all you have, okay, in your posterior. It's just very easy. If you have a way to estimate the mean for this guy, you will have a way to estimate the mean for the posterior. It's very convenient. Okay, so what is the prior for this distribution? Well, the candidate is, this one. What is it? I don't know, so I go to Wikipedia, I find it out, and the Wikipedia says it's called the gamma distribution. All right, so this is how engineering students work on problems, right? You go to your favorite website called Wikipedia and find out the distribution. All right, so this is the distribution. This is called a gamma distribution. Now, what does it mean? It means that if you have a likelihood, okay, and then you know the mean, you want to find a prior for your variance. You ask, what is the best prior for the variance? According to this rule of thumb, you're going to use the gamma distribution. Okay, so what are the meaning of these gamma distributions? I'm not going to go into detail because Wikipedia will teach you everything you need. Okay, so there are just different parameters, A and B here, and then you can show that the mean of lambda is given by A divided by B. A variance of lambda is A divided by B squared, something that I'm not able to prove by myself, but someone had proved that. Yes, question? Does the data has to be gamma distributed? No, okay. The data that you're looking at is still Gaussian distributed. However, the prior that you're using, you are asking what is the prior for my variance. And then this very interesting game says that the prior for the variance is better to be a gamma distribution. It doesn't say that your data has to come from gamma distribution. The data is still a likelihood of the Gaussian, but then by using a gamma prior for your variance, you're going to show that the posterior distribution will remain the same as your likelihood, so that you can obtain the mean and variance easily for that distribution. Okay? All right. So now you may say that, oh, this is a little bit mysterious. Then I'm going to show you something even more mysterious now. Okay, so suppose, okay, so this is just another slide summarizing if we consider this pair of likelihood and the prior, then you will show that it will take this form, and then a little bit more calculation that is just another gamma distribution. Okay, so that shows you that the posterior distribution is a gamma distribution, so finding out the mean and the variance of the gamma distribution, there are some known techniques to do so. Okay, so the more mysterious thing is this. Suppose you want to put a prior on both mu and sigma square. Okay, so you want to put a prior on both the mean and also the variance. Then you ask what is the good prior. Okay, by good, I still mean the computationally efficient prior. Then you write down the likelihood function, and then you put the lambda, because I'm assuming that lambda equals to 1 over sigma square. And then you also have the mu sitting somewhere here and there. Then you write down this expression. With a lot of magic, you can show that it can be written as a product of a Gaussian times a gamma. Now, I'm not doing any dirty thing over here. It's still a Gaussian distribution for the data. However, by recognizing this form, I would suggest, why don't we choose a prior of this form? Why? Well, because this form has the exact same form as my likelihood. Okay, and what is this? And of course, lots of genius people in the past, they have worked this out, and they show that it is a Gaussian times a gamma. Okay, and so this Gaussian times a gamma is a very good prior when you want to put a prior for mu and sigma square. Okay, now what is it called? How does this distribution called? It's called the normal gamma distribution. Again, something you can find it out on the Wikipedia. All right. So what is the bottom line message? Well, the bottom line message is that you give me the likelihood function, and then recognize the form, and then I can always find something that can match with your likelihood. Okay, that idea can also generalize to high-dimensional Gaussians, right? So the ones that I'm showing you are this 1D Gaussians. For high-dimensional Gaussians, what are the prior? The prior for the mu is a Gaussian. The prior for the covariance matrix is called this Wishart distribution, something that, again, I don't remember the formula. Prior for both mu and sigma is called the normal Wishart distribution. Right? If you're interested in, you can take up the internet, and then you can find a lot of information about these distributions. Okay, the message I want to tell you is not to ask you to derive these. Okay, it's to tell you that when you try to solve a problem, there is a rule of thumb, which is to find a distribution a prior distribution that matches with your likelihood. That's the message that I want to tell you. Right? Now, this concept belongs to a very, very big family of ideas in the statistics called the conjugate prior. This idea of conjugate prior is, it says that if you give me this likelihood, my prior has to take the same form as your likelihood. Okay? Any prior that has this property is called a conjugate prior. And then a very important thing is that this conjugate prior can, you may think that finding conjugate prior is extremely complicated because I show you the likelihood function, and then I work out all these magics, and then I show you, boom, this is the equation, right? And now the good news is that for a lot of distributions that belongs to this family of distributions called the exponential family, that includes a lot of your favorite distributions, including Gaussian, Laplace, whatever, okay? They are all exponential family distributions. Then for all these exponential family distributions, they will have a conjugate prior. Okay, so the conjugate prior is guaranteed to exist if you are working on exponential family distribution. Okay, that includes Gaussian, exponential, Poisson, a bunch of those. Okay, now if we're working on something that's outside the set, then it's a question mark whether you can find it or not. But if you're inside, then you're guaranteed to find. Okay, and so when you can go out and then try to solve some problems by yourself. Okay, here's my data set, and then I am putting some prior knowledge. The reason I'm putting prior knowledge is because I don't have enough data points. If you have enough data points, there's really no need to put a prior. Okay, so the prior I'm going to assume is that some mean, some variance depend on my prior knowledge. And then I'm going to define using these conjugate prior concept. And by using this, I can guarantee that I can have a cheap inference step, meaning that my computation will be easy. Okay? Again, I want to emphasize the last time that if you have a domain knowledge, use your domain knowledge. Okay? Even if it is harder to employ, domain knowledge is always more useful than all these computational tricks. Okay? There's always a trade-off between your domain knowledge and also the computational tricks. And you may want to find the closest approximation to your domain knowledge so that you can get a benefit from the both. Okay, so there are a lot of readings for today. So I encourage to read in this section, 3.3 to 3.5. If you read Chris Bishop's pattern recognition machine learning textbook, that's section 2.4. That's actually a pretty long section. Okay, take a look. They have a lot of diagrams, very illustrative diagrams to explain this concept of conjugate prior. If you want to have a little bit more understanding of this conjugate prior, these two are the external references. Here is a very beautiful note written by Professor Avi Kar at Purdue, ECE. So he has a very clear diagram illustrating the connections between likelihood, prior, and also posterior, how these three things work together. Okay. If you want more derivations, there are equations in the appendix, which you can take a look. Okay. So I'll see you next time.